as I say that there should be no. Hey, do you have any questions about that? Before I move on, do you have any questions? All right. Shh. Attention is required because although I don't derive any more equations here, but concept become very important. If you are very clear in concept, then this chapter is very easy. If not, then you are going to be in trouble very quickly. So let me start with an example and show you how does this moment distribution work. All right. Let's say that I want to analyze this structure, applying a moment there at B. So this is supposed to be a very straightforward exercise if you use a slope deflections. So slope deflections tell you that you need to give this a rotation angle. So there are two rotation angles. And you're supposed to use equilibrium here, equilibrium there. So two equations, two unknown, perfect. All right, but you need to go through the equations to calculate rotation angle and then substitute backward to get moments. So that's what you need to do if you want to do a slope deflection approach. So everything is about slope deflections. So I put down the slope deflection equations here. So this is the equations for the previous chapter. Now, let's go through that approach and see what we can get out of it. So here, this is joint B. So this is joint B. And on joint B, I have applied moments called M. So this is the M moments. This is the moment-free end. Action reactions. This is the moments. All right? So it works like that. So this is MBA. This is MBC. This is MCB. And finally, at this end is MAB. So let's use the moment equations, slope deflection equations. So this is 2EI AB LAB 2 times theta A, 1 times theta B, no rigid body rotations. Just put them down nicely. Just write them out very nicely. All right. I use the slope deflection equations to put them down. OK, ready? Let's go. This is moment free. So this is supposed to be equal to 0. So it tells you that theta A and theta B, they are related. We have derived this equation before. If you have a moment-free end, you can utilize the moment-free end to eliminate rotation angle at A. So theta A is equal to minus 0.5 theta B, because it's moment-free. You substitute theta A in here. So this is minus 0.50 theta B. So this becomes 1.5 theta B times 2. So it becomes 3 EI. 3 EI and this is simply just 2 times 2. So this is 4. So this is 4 EI BC, LBC, theta B. And this is simply just 2. All right, so from here, we can summarize the moment here is going to be 3 EI. Oh, I'm sorry. I'm missing a theta B. So moment here is going to be 3 EI over L times theta B. Moment here is going to be 4 EI over L theta B. So here is 3 EI over L theta B. Here is 4 EI over L theta B. OK, so we can just do a joint equilibrium at B now. So on one side, it's going to be 3 EI. And then on the other side, so that is going to be equal to the external moments, M. Cool? I just do a joint equilibrium at B. So to simplify the calculations, I call this K, B, A. I call this K, B, C. They are just coefficients, functions of rigidity, EI, and the length, L. So one is called 3 EI over L. The other is called 4 EI over L. So it's going to be KBA plus KBC theta B equal to M. So I can find theta B. Theta B is KBA, KBC, M. OK. So this is theta B. So I take theta B, put it back here. This expression give me MBA. So MBA is KBA plus KBC M. And M KBC So this KBA and KBC, they are just numbers. They are just numbers. So if you really don't care about what theta B is, if you don't care about what theta B is, if you know KBA and KBC, you can directly substitute in there to calculate MBA and MBC. So if you don't care about theta B, right, you can directly calculate the M moments directly. And this is more like distributing the moments into MBA, distributing the moments into MBC. So we give this a name. These are called distribution factor. Distribution factor. So I call this distribution factors associated with BA. So DFBA and DFBC. So if I have a way to systematically calculate distribution factors, then I can directly distribute the moments into the components and then just forget about calculating the rotation angle completely. So distribution factor is the first important concept for moment distributions. So imagine this. I look at the structures. If I can calculate directly the distribution factors for BA and distribution factors for BC, then I can just take that moment, multiply this, and then put it here. Take that moment, multiply this distribution factors, put it there, and I can resolve this moment here already. For this particular structure, this side is moment free, so we don't have to worry about this moment here because moment is equal to 0. Now, how about this side? What is the moment there? So you can take a look at this and that. You see that whatever you get there, if you just multiply by 1/2, then this is 2 times. So whenever you get moment here, all you need to do is just take that, multiply by 1/2, and then put it here. You have the moments over there. That, of course, is because you have a clamp conditions. So the clamp conditions, the relationship tells you that the moment here is 2 times of the moment here for the clamp conditions. OK, so that is roughly the idea of moment distributions. OK. So let me show you how it works now. All right, I'm going to use the same. All right, shh. You might need some time to digest. The main criteria or main theme is I'm trying to skip the calculations of rotation angle completely. So I'm going to skip this part. All right, knowing that it's going to be substitute here to get the moment, substitute here to get the moment. So that I just did. So I call this distribution factors. And you can see that distribution factor is a function of K. Now, we define K as a rigidity or stiffness of the components. OK, so I'm going to see whether I can calculate directly the moment here and moment there. So as we just discussed, this is called MBA. This is called MBC. So I know that MBA is going to be a function of distribution factors BA times the external moments M. MBC is going to be distribution factors BC times M. So the key here obviously is distribution factors. So let's go for the distribution factors, BA. So according to what we just defined, distribution factor is summations of stiffness at that joint, and then on top will be which part of the components that you're looking at, you check on that part. So you're looking at BA, that part, so you should put stiffness BA on top. At the bottom here is everything connecting to B. So it should be BA plus BC. You have only two components. Now, KBA, as we defined, is 3EI over L. 3EI over L. So we are assuming that they have the same rigidity, same length on both sides. If they have different rigidity or different length, then of course this will be changed. So 3EI over L, and here is 3EI over L plus BC, 4EI over L. So if EI, they are all the same, L, so this becomes 3. So this is the distribution factors, 3 over 7 for BA. So next is distribution factor BC. Denominator is the same. And on top is BC. So you see here, right? So KBC, if KBC then is 4EI over L. So 4EI over L, this is 4EI over L. If the far end is clamped, it's 4EI. If far end is free, then it's 3EI. It goes like that. So this is 4EI over L. So this is 4 over 7. So if you follow this concept, you go calculate the distribution factors, and then you just take the distribution factors, put it here. Then you have this 3 over 7m, and this is 4 over 7m. OK? So this is what we got. I have an external moment applied here. And I go through the distribution factors. I calculate this. And I calculate this. So during the calculations, I don't see rotation angle. I directly go for the distribution factors. So look at the far side. This is moment free. So moment here is equal to 0. This is the clamp end. This is the clamp end. And as we just put down in the beginning, the moment on the clamp end is half of whatever you get from the other side. This is 4EI over L. This is 2EI over L. So whatever you get there, multiply 1/2 is the moment at the far end, if that far end is clamped. So it tells me that this moment is 2 over 7 m. So the rest, then you just figure it out using local equilibriums. So the rest is just local equilibrium. Okay. That solves the problem. If you don't care about rotation angle, you can directly come over the calculations of distribution factors and directly distribute the moment right at the joint, and then look at the clamp. Then you just multiply whatever you get there by 1/2, put it there, and that's it. Very clean, simple, straightforward. But it's based on slope deflection equation, though. OK, so it seems that the key here is this. The whole operations depends on the calculations of distribution factor. Fortunately, the distribution factor is based on K, and there are only two K values we have to worry about. So the K value is the key to this approach. So K is either equal to 4EI over L or 3EI over L. It only takes on these two values. It's either 4EI over L or 3EI over L. This is the most critical part of this whole approach. It either takes on 4EI or 3EI. Depends on what? Depends on the far side conditions. So 3EI over L should be given if the far side is moment-free. If the far side is moment-free, then K is 3EI over L. If the far side is clamped, this is clamped, then it should be 4EI, which are based on slope deflection equations. So there are only two values, again, for K. Either it's 4EI or 3EI. If far side is moment-free, it's 3EI. If far side is clamped, then it's 4EI. So imagine this is more like a spring. So if you want to rotate this part, this is moment-free. It's much easier than rotate that part, because that part has a clamp end at the other end. So imagine that you need to apply a torque. You need to bend this part and bend that part. It's much easier to bend this part than bending that part. depends on the far side conditions. Okay, so summary is it will take on 4 EI if the far side is claimed. You take on 3 EI if the far side is free, moment free. Cool? All right. Ready for the challenge? I used to give this problem as the final exam. Right. So I used to give this out as a final exam, but I saw that I want to give away 20 points, but unfortunately, most of the people cannot get this. Supposed to be giveaway, but become a killer. If you can get it, if you know what I'm asking, you can get this in like less than 3 minutes. If you don't know what I'm asking, then you cannot get it. So of course, you need to plot the shear force and bending moment diagrams. So you ready? So it's actually like this. I'm going to use moment distributions. So OX, X means A, B, C, D. So I can directly get the moment. I can directly get the moment here. This is MOA, MOC, MOD, MOA. I can directly get them if I know the distribution factors. So I'm summarizing into one equation. So distribution factor OX times M. So moment is applied like this, right? Like this. So the key is distribution factors. So let's go for that. Distribution factors OA, one by one. So what is distribution factor OA? It's going to be KOA, stiffness of OA. And here at the bottom should be the summations of all the stiffness that connect to that point. So it should be KOA, KOB, KOC, and KOD. All right. That's distribution factor. Now, there are only two possible values for K. Depends on whether depends on the far side conditions. So either 3EI over L or 4EI over L. So you look at the far side conditions. This is OA. Far side is climbed, so this has to be 4EI over L. So 4EI over L. KOB, 4EI over L. KOC, 3EI over L, because far side is moment free. OD, 4EI over L. So eventually, you will get 4 over 15. Good. Same thing for similarly for K distribution factor for OB, distribution factor for OD. The far sides are all clamped, so they should have the same stiffness. The remaining one, you don't need to calculate actually, because the distribution factors for all components add up should be equal to 1. Distribution factor add up should be equal to 1, you see. So the last one got to be 3 over 15. All right, cool. So I know this is 4 over 15 m. Here is 3 over 15 m. Here is 4 over 15 m. And here is 4 over 15 m. All right? And then the far side. If far side is clamped, then you just pass on 1/2. Far side is clamped, pass on 1/2. Clamp. Moment free. That's it. I get all the moments now. So you can do this in a matter of like a few minutes. All right, do you have any questions? So the key here is the distribution factor. How do you calculate distribution factors? And how do you calculate the far side moment? So far, the cases are kind of simple and straightforward. So with that, then you can calculate shear force, no problem. Good, cool. So if I ask you these questions now, can you handle? All right. So if I ask you these questions, can you handle? So what do you think? You want to give it a try? So if I ask you, of course, I always try to challenge you, right? I couldn't give you that questions now. So if I want to challenge you, no, I'm sorry. I don't teach structural analysis next semester. See you next year. All right, sure. Oh. Last time? What did I ask you to do? Deformations? Okay. Oh, different length, huh? So I asked you, yeah. So what do you think? Anybody try this out? Nobody? Oh, that's good. That would be a very good final exam questions. Okay. So who want to give this a try? Shh. Now, if I give you these problems in the final exam, I will classify this as an easy problem, all right? So this is supposed to be this is out of my compassion to you. Yeah. Okay. You know how to do this? Imagine. Use your structural knowledge now. You can do it, actually. You just need to think hard a little bit. Yeah. Why don't you look at this component first? Cut it there, and what do you have? I'm just trying to give you a very quick confidence building. So what do you have? If I cut, I should have force and bending moment, right? Action reactions, the bending moment will be applied over there. Ah, okay, so you can just forget about that. All right. All right. Isn't that smart? All right. Okay. Huh? Shh. All right. Shh. All right. Now, you have seen this support. Shh. Now your task is trying to distribute this into the component, right? So you need to set up distribution factors for each one of them. Shh. Then you know how to set this up. You know how to set this up. Shh. You know how to set this up. This is 3EI. This is 4EI. This is 3EI, 4EI, 3EI, 4EI, and here. So here's questions. This is a roller. Shh. So should it be given 3EI, 4EI? 3EI. Shh. See you next year. All right. Shh. So, 3EI or 4EI? See you all next year. Zero, yes, precisely, zero. Shh. Shh. It just cut it there. There's no force there, right? Only actual force. So the moment there has to be equal to 0. Yeah? So moment has to be equal to 0. So no EI, no EI over L. So 0. All right. See you Friday, all right? So